So this is a super short one, and this is just about cutting a circumference in half. So to cut a circumference in half, and actually this is one where even if I don't tell you the proof, you probably just do it in this way, right? This really, I can't see any other way of doing it. So you have a circumference, not necessarily half the circle, but it's some part of the circle, and we have a line. Well, we have the endpoints firstly, A and B, and we're going to join the endpoints into a line, right, like this, right? So how are we going to cut the circumference in half? Well, we're going to cut the line in half and then just like construct a perpendicular at that midpoint, right? And so this is how you would do it, even if I didn't tell you how to do it. Right? So this is we're going to find the midpoint, and we're going to find the midpoint using proposition 110, right? Tells you can find the midpoint C with these two parts being equal. And I'm going to put the label somewhere else because I'm going to draw a line through it. So this is C. And we're going to draw a perpendicular from C, perpendicular to AB from C, and have that perpendicular meet the circumference at D. So go like this, straight up, D. And we're going to join, of course, A and D, and D and B. Okay, so I'll just mark this in. This is a perpendicular line here. And the proposition from chapter book 1 that allows us to do this is proposition 1.11. So this is proposition 1.11. Gives us that perpendicular. So the proof is, now that we have this construction, the proof is just to show that the arc or the circumference AD is equal to the circumference DB. And so more notation, this part of it I'll call AD, and this part of it I'll call DB. Okay, so the claim is that AD, the arc AD is equal to the arc or the circumference DB. So proof. So we've got two triangles here. The proof is just going to be showing that these two triangles are equal or congruent, and therefore all the corresponding sides are going to be equal, and then we can go from there. So look at these two triangles. They share a common side. The common side is CD, and we've constructed C as the midpoint of AB. So since AC is equal to CB, right, because we've constructed C to be the midpoint, and DC is common, I guess, well, also the other thing that's equal is that DCA and DCB are equal. Are equal. In fact, they're equal to both equal to right angles. Okay, so by proposition 1.4, we've got that these two triangles are congruent, and in fact, we can just conclude that the thing that we want is that AD is equal to DB. AD is equal to DB. Okay, and then the what we want is really just application of proposition 3.28, which says that once you have these two lines being equal, the circumferences that sit on these lines are also equal. So proposition 3.28, equal straight lines. So the equal straight lines are AD and DB. Lines cut off equal circumferences. All right, so hence AD, the circumference AD is equal to the circumference DB. That's it.
Awesome. All right. Proposition 31. This is actually pretty serious. I like this. So in a circle, the angle in a semicircle is right. So remember that when we cut off any circumference, we have the same angle, meaning if you join the points, a circumference meaning a part of the circle that's cut off by a line. If you cut off that part of the circle and then draw an angle made by the endpoints of the line and any point on the circumference, it's going to be the same angle. We discussed that 2 weeks ago, I think. So that's the angle of the segment, if you like. And now we're talking about when you take segments or circumferences that are more or less than a semicircle, what those angles are. So it's a very natural question. And the first statement is that if you take a semicircle, the angle you get is a right angle. I'm not going to say it the way that it's written in the book because it's sort of incomprehensible the way it's stated, but the angle in a semicircle is a right angle. The angle in a segment less than a semicircle is greater than a right angle. And, well, I guess in modern terms I would just put it in brackets, right? So we'll do that. So this is a modern math way of having multiple statements with small changes. So the angle in a segment less, in bracket greater, than a semicircle is greater, in brackets less, than a right angle. Just for anybody listening who isn't used to parsing sentences like that, often it's not even explained in a math book, right? Like it's something that you sort of actually just need to have someone tell you. The angle in so you read less with greater, and then you read a second version of the sentence where you read the things in brackets. So the angle in a segment greater than a semicircle is less than a right angle, is the second statement there. All right, so proof. Here's our circle. I won't write down all the labeling in words, I'll just say it. So E is the center. I have A here. A is an angle made by the semicircle. So here's B, here's C. I'm going to join those there. And so the first thing I need to argue is that BAC is a right angle. Okay. The angle ABC in the segment ABC, so this is a segment ABC, and the angle ABC is in that segment, and okay, I guess it's just a way of using, I need to explain how this one picture actually argues for all the sort of relevant things. Maybe I'll do that now. It's not really part of the proof. So I'm going to prove that this angle in red is a right angle. That proves the first statement. If you look at the segment ABC, that's greater than a semicircle. And so I need to prove that this angle here is less than a right angle, and then I'm going to add further a D, which is here. Now this segment ADC, the only reason I'm choosing D in this particular way is to make ADC a segment which is less than a semicircle. And so the final statement will be to prove that this angle here is greater than a right angle. Okay, so this diagram now contains all the ingredients I need to prove the things I need to prove. All right, so let's get about proving that BAC is a right angle. Okay, so we join AE. Then, well, note that BA can be extended. Just keep going to some point F. All right. Join AE, then extend BA to F. So ABE equals BAE. Why? Well, because these are the same length, they're both radii. And for the same reason, EAC equals ACE. These are both proposition 1.5. So BAC equals ABC with ACB. Let's see. So this here is equal to, it's made up of these two pieces. Those two pieces are the same as those two pieces, right? Okay. But the exterior angle FAC also equals that, right? The sum of the opposite and interior angles. So ACB, ABC, that's, I don't know, 1.32. Okay. So we have FAC and BAC equal, and together they make two right angles. So that shows you that BAC is right. Okay, so that's the first claim. Yes, that's quite nice. For the second claim, so now we're talking about ABC, and we want to prove it's less than a right angle because the segment is greater than a semicircle. So ABC, well, in the triangle rather, in triangle ABC, the angles ABC and BAC are less, taken together, are less than two right angles, because that's true of any pair of angles in a triangle. And BAC is a right angle. We just proved that. So ABC is less than a right angle. Right, ABC and wait, let me be sure I'm saying something sensible here. In the triangle ABC, the angles ABC and BAC are less than two right angles, yes. And yeah, that's right. Okay, so ABC is less than a right angle, which is the claim I needed to show, right? Okay, so that's the second claim, so that's easy. The remaining one is sort of the more interesting one. So for the final claim, we consider the parallelogram ABCD quadrilateral. Sorry, it's not a parallelogram. Now we know something about quadrilaterals in a circle by proposition 22, the book we're reading. Opposite angles of quadrilaterals in circles add to two right angles. Opposite circles. Angles add to two right angles. While ABC is less than a right angle. So that means the opposite one, which is ADC, must be more. Yeah, this is clever. I'm not sure I would have immediately thought to use this. Yeah, then there's some waffle in the book that goes on past this. I don't really get the point of that. We're done.
Cool. Awesome.
Yeah, I like this one. We're starting to have quite a few different tools at our disposal, right? Which makes it more exciting.
Yeah. So, do you think we should press on or stop? We've got 5 minutes, but 32 is kind of long. We're going to get it cut off if we stop on time.
Yeah, I think we can just leave it to next time when we have a look at 32. Yeah, that's...
When are you heading out to your trip?
Yeah, I leave... well, next week I'm actually in Sydney for an event, so I also won't be here.
All
so
right.
we'll take... So then the week after I'm in Oxford, and the week after that I'm on holiday. So we'll take a month off.
All right. So this is the same break as SLT.
That's right.
Mentioning in the channel. Yeah. Cool.
So yeah, see you in a month again.
Yeah. Have a good trip. I might. So you guys are having talks in SLT. I might drop by if I have, because I think it's at 10 o'clock now. Well, you don't know that. I think it's at 10 o'clock now for me. But anyway, so next month will just be ad hoc discussions.
That's right.
And you'll be kind of traveling as well. Okay, cool. Well, have a good trip, Dan. If I don't see you here and there in Roblox.
Yeah. Thanks. Take care.
Cheers, man.
Yeah.
Bye bye.